Hello guys, welcome back. So in this tutorial we are going to see how we can compare the experimental data and the predicted data from the Johnson-Hook model which we proposed using the real-time experimental data. Why we need this procedure means when we are developing or when we are proposing some JC model, we have to know how much good the mathematical model with respect to the real-time experimental data. I will show some example which we used before, like this is the paper data we used for data extraction. Also this is the data we used to build the Johnson-Hook model. So as you can see here, they made some comparison plot. In this plot you can see there is experimental data in terms of points and there is a predicted data in terms of line, which means that they have the real-time experimental data and they extracted the predicted data from the Johnson-Hook mathematical model and they made a comparison to show how much good the prediction data with respect to the experimental data. So this kind of comparison is necessary either if you want to write some research paper or if you want to do some simulation work. So let's go and do the comparison process. So for that, what I did, I just go to the Johnson-Hook model constant. So as you can see here, this is the model which we developed from the last tutorial. So let's keep this one and also keep the experimental data. So in this process we are going to use two things. Either we will use the correlation coefficient or we will use the coefficient of determination. Sometimes people call it as R square value, and there is one more, root mean square error value, because these are the metrics that can be used to explain the empirical model. Because as I said before, the Johnson-Hook model is kind of an empirical model that developed based on the real-time experimental data. The empirical model means it's kind of approximated mathematical model which replicates the real-time experiment data distribution or the behavior, how the data distributed on the space. So if you see here, there is a three kinds of correlation value, which is positive, negative, and then no correlation. So this kind of numerical number can be used to explain how good the prediction data with respect to the experimental data. So we will see how to calculate these values and how to compare that one with the real-time experimental data. So for that, what I did, I made one tab and I arranged all the experimental data, and now we are going to make a prediction. So for that, let's go and do some process before we move on to the final steps. So first we have to calculate the Tstar, which is like based on the reference temperature and melting temperature and the chosen temperature. So as we saw before, if you go here, you can see the reference temperature was 1323. So keep that one in mind. So it is going to be the reference temperature. Let's type it here. So reference temperature is going to be 1323 Kelvin and the strain rate is going to be, let's go back and see what was the strain rate. It was 10. So keep it 10. So using these two values, we can calculate the dimensionless temperature as well as the strain rate. So let's calculate the temperature, which is T star. So if you go here, let's make a parenthesis. We are going to make first one 1323, and this one we can do it like, you know, based on this temperature, or we can directly do it here. Okay, let's do it like one by one. So first make a 1323, which is like this one, and then the reference temperature is going to be here, and then divide by the melting temperature, which is going to be this one. So we have to make like this, otherwise the data will repeat. So you have to be more careful when we are choosing this kind of one cell for the whole calculation process, otherwise there will be some problem. So it is T0, then we have to repeat 4 times because we have a 4 temperature. So in this case you can change this to 1373 and then enter, and you can give this one to 1423. Okay, and then you can do 1473, enter. So now we got the 4 value for the 4 temperature, and this strain rate from 0.01. So we are going to develop only one strain rate star. So this one is going to be like we can make a ln, which is much better, otherwise it will be confused. So this one is going to be 0.01 by, which is the reference strain rate, G21, then enter. So everything is ready. We need these two before we proceed to the final step, so we did this one here. So let's go here now. So we have to make these three parentheses, so we have to be so careful. If we miss some value, then there will be a problem in the final results. So be careful with the data selection. A plus the B is going to be C 3, so make that one clear, and then multiplication of strain, which is S. So as I cannot select this one, I'm just directly selecting that one. So power, the N is going to be this one, so star. So we completed one. Let's make the second parenthesis, which is 1 plus C, which is here, and then star, and then you can multiply strain rate. These values are going to be fixed, so make sure that you properly do the process. And the final one is 1 minus this one. So this is going to be the same value for everything. So there is some problem. S1, sorry, like this one is S3, not S1. That is why the problem happened. So just delete here and keep it the value. So now it got it, because this was supposed to be S3. I made a mistake by selecting this one as S1, so there was no data. So make sure that you did everything well, and escape, and then you just drag it down. So you can see everything is okay, because these cells are fixed. Only the S7 is going to change. That is why it works really nice. So now what you can do, just copy this one, and when you are pasting here, just paste it as a P, and then do the same. So now everything is updated, but we got the same value, because here we have to change something, which is the temperature, which is the Tstar. So just go here. In the last one, just change 24, because that is the next one. Just click and then enter. So now you can see the values are changed. Then do the same thing, copy and then paste it, and then drag it down. Then finally go here and choose that one to 25, and then you can do the drag again, and then copy and then paste it, drag it, and before that you can do change this to 26, and then drag it. So now everything is done. So this is the experimental data, and this is the predicted data. So now we completed everything. Let's make a graph. Go here and go to the scatter plot, and then select the select data, then add the first one, which is going to be this, and then this. So we got it. Just say 1323 Kelvin for your reference. Just call it as a E value, like experiment, not E value actually. So next, go here and then calculate this one and this one, 1323, which is prediction. Okay, then 1373 Kelvin E, and then do the same thing. Let's do the process very fast. So it seems everything working really nice. So let's do one more thing. Okay, so now we did, and you can see how it works. And if you don't like, you can also change the plot style by going here. Yes, so if you do this one also, you can clearly see how good the data with respect to the prediction data. So these are the thing you can do when you are making the comparison. But in some cases what you can do, you don't need to go for any two kinds of thing. Either you can go with only scatter plot, or you can go with a line and scatter plot. In that way you can clearly explain how the prediction data with respect to the experimental data. So finally we got the data from the experiment as well as from the prediction. So let's compare this graph with respect to the published research work. So for that, just open the paper, we have the data here. For that, just go here and then snipe it out so that we can use it. You can just make a graph of this figure, so that can be done like this. So but if you see here, the data looks like coming down, but in our case is going up, which means we made some mistake in the calculation. So let's go and check here. So the first parenthesis a b and epsilon power n, and then 1c ln of strain rate, and then 1 minus the temperature. Yeah, here we missed the parameter which is m. So choose that one. It automatically shows if you miss the data, you can see here we selected all the model constant but we missed m. So it is very clear that we made some mistakes in the calculation. Then click that one and then go here. So before that, what we can do, just click m and then make a dollar sign. So it's okay. Then why there is no change in the value? As you can see here, we added the m model coefficient into all the calculation. So now everything looks fine, but still if you see the two graphs, it looks a little different because they made the experimental data in terms of scatter plot and predicted data in terms of line plot, but we did the opposite. So now let's change. So this one to the line data, and then the experimental will be the scatter plot. So then you can see how differ it is. So change to the scatter, and then the prediction will be the line plot. Do the same thing for everything. Then experiment is okay. Then this one from the prediction, so that has to be line. So this has to be line, and then the final data will be the scatter plot. So now you can see everything is clear and the prediction looks exactly similar, because they also made like a little bit compressed image. As you can see here, the line graphs are from the prediction, as you can see here, and then the scatter plot from the experimental data. So it looks same. So what they published in the research paper, we exactly replicated in our process also. So the tutorial is fine and everything what we did so far is great. So now let's go and see how we can make the matrix calculation, which is r square and then root mean square error. So for calculating r square and RMSC value, we need some equations that we can be seen here. So that just copy paste here so that you can understand how we are going to make a calculation. So at first step, what we have to do, just copy this data and arrange it here. Just type experiment and then prediction, or you can just call it as prediction like this. And then we are going to do the calculation process, because otherwise we will not understand how it works. So we have to calculate the sum of error and then sum of total error. So this is residual error and this is total error. For that, just copy paste all the experimental data and arrange it in one column. So paste it here. This data we can just simply copy paste. So if you copy paste like this, then you can see sometimes there is some changes in the value. So make sure that you stick to the proper copy paste option like this. Use this specific option which says 1 2 3 paste, which is like just paste the values. So now everything is okay. So we need a mean value. So just to calculate here the average, which is going to be the mean of the whole experimental data, and then enter. It's okay. So this is the mean value. And then let's calculate this one. So first we are going to click the prediction and then minus the mean value, which is going to be stable for all the calculation. It's not like a stable, it's same for all the calculation. Just square it, then just copy paste it here. So instead of doing the prediction, we have to do here the experiment data, enter it. Okay, then we have to make a sum of the residual error and then sum of total error. For that, just go here and then sum this column, and then here do the sum of the total error, which is this column. Now you got these two value. We just have to simply divide the residual error by the total error. So we got 73, which is the 73% correlation, which is more than 70%. We got the correlation. So this is the R square value we got for one particular conditions. And some people calculate R square value for the entire test condition. But from my advice, better to calculate the R square value for each condition, so that you can more explain how your prediction data with respect to the experiment. So now we have to calculate root mean square error. So for that, you just need the experiment and prediction data. Just to go here. So prediction minus experiment and then square that one. So this is that one completely. So we got this data, then we have to sum it. This one, so sum of this one, the whole column. Okay. And then we have to average it by we got like a 3 6 9. So the total number is going to be 36, I think. So enter and then take a square root, which is this one. So this is the root mean square error. So 4.2 means this is the megapascal, because as you can see here, we just simply minus the prediction stress from the experimental stress. So this is the 4 megapascal. So which means that when we calculate the stress values from this prediction model, we can see each point is average of 4 megapascal. So the prediction gives the error of 4 megapascal in each point. So that is how the root mean square can be explained with respect to this calculation. So that's it. This is for the one condition, which is like fixed strain rate with respect to all of the temperature. You have to repeat everything for other strain rate cases, and you can make a comparison of this figure for all other strain conditions with respect to different temperature. And you can also make R square and root mean square error. By way of doing this, you can write a paper very clearly, and you can explain how good your model and how the model can be used for simulation. So this is what I was planning to explain through this tutorial. So I hope this tutorial helps you to make some comparison and some metrics calculation that can be used for paper writing. So thank you so much for watching. We will see in the next tutorial. The next tutorial will be about the MATLAB code, and in that MATLAB code I will explain how you can calculate the Johnson-Hook model parameter, and how you can make this kind of comparison plot, and how you can calculate the metrics directly just by one click, which means it's kind of time saving, and you can use the code for other material also with respect to the same experimental conditions, and that will kind of save your time when you are spending some time on calculating the Johnson-Hook model or making some plot, and it will be like time saving. So let's see in the next tutorial, and thank you so much for watching. See you soon.